Welcome to everybody. So, I don't know anything about law, but because I'm a planetary scientist, Samantha asked me to introduce a bit the topic, to discuss what resources are out there and attracting the interest of states and private companies, and what are the technological prospects to use them in the near future. So there are really two kind of bodies which are of interest for space resources. One is asteroids and the other is the moon. So asteroids are small bodies that orbit typically between the orbit of Mars and Jupiter, so they are quite far away. But some have orbits that intersect the orbit of Earth, so they come close to us, and it's relatively easy and cheap to come close to them. So why are asteroids interesting as space resources? Because asteroids are rich in some elements that are very rare on Earth, and so they are very precious, like the platinum group elements, gold, silver, nickel, cobalt, rare earths. So all these minerals that have value or have some utility in industry. And they are rare on Earth because the Earth differentiated into a rocky mantle and an iron core. And during this process, all these elements went into the core. And the core is thousands of kilometers deep, so we cannot reach it with our mining technologies. And the only elements that we can find of this kind in the crust are the little bit that has been delivered to the Earth after its differentiation in what the geochemists call the late veneer. But asteroids are much richer in these elements. So asteroids can be divided into broad groups, those which did not melt and those which melted. So those which did not melt are related to a class of meteorites that are called chondrites. And so we know what they are made of. And in these asteroids, these rare elements on Earth are actually 100 times more abundant per kilogram, per unit mass. The asteroids that differentiated also sequestered these rare elements in their cores, but some of these differentiated asteroids have been broken up in collisions. And so unlike the Earth, the core of these bodies is not deep inside the body, but it's exposed to space. And these are the parent bodies of iron meteorites. And so again, we know what they are made of, and there, the rare elements on Earth are 1,000 times, up to 1,000 times more abundant, so per unit mass. In addition to these rare elements, some asteroids, which are related carbonaceous, so they are related to carbonaceous chondrites, are rich in water. So water, of course, is not very valuable on Earth, so we will never go to space to bring water down to Earth. But it's useful for in situ use. So this is called ISRU, so in situ resource utilization. Why is water useful? Well, it's useful because water is useful by itself. Imagine astronauts have to drink water. But in particular, it's useful to be dissociated in hydrogen and oxygen, which can then be used as fuel for space rockets. So if you want to go, for instance, to Mars, then you need a lot of energy to bring the rocket to Mars and back. And then you need a lot of hydrogen and oxygen as fuel, and bringing it from the ground to the space would have a gigantic cost. In addition, there are some other minerals which are also common on Earth, but if you want to fabricate something in space, it can be cheaper to use them in situ than to lift them from the Earth's gravity. So this diagram here gives an idea of the value of these elements that we can find in asteroids. So for platinum, gold, nickel, cobalt, these are the prices on the market. So, talking about $10,000 per kilogram. And so these elements, because they are abundant there, if one can extract them, could be useful to bring back on Earth. For water, this is for use in space, locally. So water is worth a few cents per kilogram, of course, on Earth. But in space, it's almost $10,000 per kilo. So you understand it's more attractive to get water in space, to be used in space, than to lift them from the Earth's surface. And so, of course, these numbers are great, right? And that's why people, companies, and states are becoming so interested in exploiting asteroids for space resources. And this other diagram shows the value that an asteroid can have. So for instance, the carbonaceous asteroid of 1 kilometer, just because of its water resources, about 10% in mass, in principle, it's worth $1 million billion. Of course, supposing that you are able to extract up to the last drop of water, which will certainly not be the case, but these numbers are enormous. A metallic asteroid of 500 meters, because of these rare earth elements that it contains, 1,000 times the concentration that we have on Earth, can be valued of the order of 10,000 billions. So these numbers are really attractive. Of course, exploiting space resources, in particular from asteroids, is not easy. Because on Earth, it's true that these elements are rare, but they are not uniformly distributed. The geological activity of Earth concentrated these elements in some places. So for instance, gold is not uniformly distributed in the crust, but is concentrated in some veins. And when you get the vein, it's quite easy to extract it. And this is what motivated, for instance, the gold rush, California, Alaska, and so on. On an asteroid, there has been no geological activity, so these elements are uniformly distributed in the asteroid. So if you want to extract them, you have to process a lot of material in order to take what you need and disregard what you don't need. So a lot of mass has to be processed with an industrial-like style process in order to get these resources. And is this realistic? So asteroids, as I said, are small, in particular those which come close to the Earth and are easily reachable by our satellites. And so landing on an asteroid in a controlled manner is extremely complicated. So we recently have been able to take samples from 2 asteroids, and this has been done by the Japanese Space Agency, JAXA, and then later by NASA Space Agency. But these samples are collected in a touch-and-go process, as you can see in the movie. So you don't land on the asteroid, just the probe comes, touches the asteroid, takes a sample, and flies away. So this avoids the problem of controlling the landing. And the result is that you get almost nothing, right? The JAXA space mission collected 5 grams, and the NASA space mission 121 grams. So it's like ham, you can get from your budget. So it's really very little. So now for science, it's great. It's enough. But of course, for exploiting minerals, we are orders of magnitude away from what would be needed to be done. The only attempt of a controlled landing on a small body was tried by the European Space Agency, ESA, on the comet 67P. This is a body of 4 kilometers, so bigger than a typical asteroid crossing the orbit of the Earth. And the Rosetta mission tried to land a probe on the surface of the comet called the Philae. So that was a sort of failure, because when Philae touched the surface of the comet, control could not be kept. And so the lander started to bounce off the surface of the comet from the bottom left to the top right, and in an uncontrolled manner, and eventually stopped when it crashed into a boulder. And it was upside down. So we could still use it for scientific purposes, for some of the instruments, but of course that would not have been able to carry any significant extraction. So it's very complicated. Today, I would say it's impossible, but as you know, as SpaceX told us, taught us what is impossible today may become a routine the day after. So who knows? Now, what about the moon? So the moon is the opposite of the asteroid. So if the Earth has very few of these valuable elements, like rare earths and gold and so on, the moon is even more depleted in these elements. So we're not going to the moon in order to take these precious minerals, but the moon can be used in order to support the human installation on the moon. Again, if you want to build a human basis on the moon, you can bring everything from Earth, and it costs a lot. Think about the price of water in space. If you can take these elements, the material that you need to build this basis on the moon, of course, in principle, it can be much cheaper. So water, of course, there should be astronauts there, so they have to drink. And there is no water, I mean, there are no rivers, no lake on the moon, of course, but there is a little bit of water ice at the poles, and that's why the space agencies speak of placing the human bases near the lunar pole. There is some oxygen in the regolith, and then there are other minerals that are iron, aluminum, magnesium, titanium, and so on, which are quite common on Earth. They are also there, and they can be used to construct some of the infrastructure needed on the moon. The only resource on the moon that would be valuable to bring back to Earth is helium-3. Helium-3 is potentially a fuel for atomic fusion on Earth. So atomic fusion is the process that makes stars shine, and it's the holy grail of nuclear research, because if we were able to replicate the process in stars, we would have cheap energy, totally decarbonized, and without the risk of radioactive waste. Now, of course, we're still far from making nuclear fusion on Earth, even in the labs, but you know, things are progressing. And the roadmap to nuclear fusion on Earth, it seems so the stars do it starting from hydrogen and producing helium, and this is quite hard. And an intermediate step would be to start from helium-3, which is an atom of helium that has only one neutron, and collide them with each other, which would produce a helium-4, so the stable helium, which has 2 protons and 2 neutrons, liberating 2 protons, or colliding an atom of helium-3 with an atom of deuterium to produce again a normal helium and another proton. So these are reactions that are less favorable than fusing hydrogen into helium, but still produce energy of the order of 12 or 18 mega electron volt per collision, and so would be and probably easier because the potential barrier to outcome is smaller. And so this could be the first kind of reactions used in fusion power plants on Earth at the horizon 40, 50 years. Now, helium-3 is inexistent on Earth, and it exists only on the moon because it's produced by the implantation of the solar wind, so particles, protons sent by the sun, on the lunar regolith. And the concentration is just a few parts per billion, higher in certain soils on the moon, and it's 0 elsewhere, it's 0 on the Earth. So, of course, the extraction is energy sensitive, and these nuclear reactions, the plants don't exist yet on Earth, but in the future, this may be an important resource. So, to summarize, asteroids versus moon. So the moon is accessible, it's easier in some sense to land on it because there is some more gravity, but it's basically good only for in situ exploitation of these resources. So this will be valuable as long as the space agencies decide to install bases on the moon, which is planned, but it could be, could step back from that. It's a scientific enterprise, basically, not an economical enterprise. And the only resource that we can bring back from the moon on Earth is helium-3. Asteroids, instead, are huge water reserves for space flights, but it could also be useful to get minerals that are rare on Earth and very valuable, so material that has to be collected there and brought back to Earth. Now, a few words about the roadmap. And so this is what agencies publish as, so is it realistic? Is it wishful thinking? I don't know. I think it's a little bit optimistic. Think about, according to the NASA roadmap to the moon, astronauts should have been back on the lunar soil one year ago, and we are still far from achieving that. So take this with a grain of salt. But without reading it in detail, basically in the next 10 years, the idea is just to make some little experiments and prospection. No more than that. In between 10 and 20 years, start to use some lunar resources as a test, as a practical test, and still keep exploring a bit about the possibility of exploiting asteroids, and then go into a full scale of use of lunar resources in the next 20, 35 years, and starting to do tests of exploitation of asteroids, and the really industrial exploitation of asteroids would just start in the next 35 to 50 years. And as I said, this is probably optimistic. So in conclusion, there are clearly valuable resources in space, but they are not easy to collect and to use. Certainly their exploitation is unrealistic in the near term and might become realistic in 20, 30 years. So your job, making a legal framework for the use of these resources is definitely less urgent than for the use of Antarctica or deep sea resources, as Samantha said before. But on the other hand, it's good to use this time at your use, because there is some time in order to set up a really binding framework. So from my point of view, as I said, I'm not an expert in laws, but of course I study space, so I'm sensitive of what is out there, like I'm sensitive about our nature. The goal really is not to block any exploitation of space resources. I think this would not be realistic and would be rejected. But what is important is to put enough to develop a legal framework so that the future exploitation of space does not turn into unstable, unsustainable development like unfortunately is on Earth. Okay, thank you very much.